Multivariable functions. The goals: we want to define functions of several variables numerically, algebraically, and visually. So visually, graphically, same thing. We want to sketch the graph of a function of two variables. We want to sketch the level curves of a function of two variables, and we want to sketch the level surfaces for a function of three variables. In Calculus 1, you talked about functions on R2, didn't you? R2 being the xy plane. And you spent your whole time analyzing functions of a curve y equals f of x in the xy plane. You learned how to take derivatives of those curves, integrate, and do lots of fun applications, right? Well, that's in R2. Now we're in R3. And so what are the functions going to look like in R3? Well, as you might expect, the function notation will be similar, but this time we're going to have inputs of two variables. I need to change that y to a z. We're going to have inputs of two variables and an output variable of z. So, okay, if you think about it, in Calc 1 you had one input variable, right? And one output variable in your function. For the most part in Calc 3, we're going to have two input variables and one output variable. And we actually will have functions over R4. I don't think we'll go much beyond that. In fact, we'll stick mostly with R3, functions that we can graph in R3. But as you might imagine in R4, we're going to have functions of the form w equals f of x, y, z. So you have three inputs and one output. And of course, you could keep going, but we won't, not in this class anyway. So let's look at a bunch of functions. F of x, let's start with f of xy rather, equals x squared plus y squared. That would be a real valued function. Now, you can always replace, remember how in R1 you can always replace when in y equals f of x, so if y equals like x squared, remember you can always replace y with f of x or vice versa? Well, it's the same thing here. You can replace f of xy with z and vice versa. So f of xy equals x squared plus y squared, same thing, or any other letter you want to use, except for x and y. Or z equals x squared plus y squared, same thing. Okay, that's a two variable function. For any particular values of x and y, you get a number, don't you? For any particular values of x and y, you get a number. For instance, the extension of the usual function notation that you're used to applies here. So if I asked you to find f of 2, 3, how do you think you would do that? Plug in 2 for x and 3 for y. Right? So what would that be? 4 plus 9, 13? Yeah. F of 2, 3 is equal to 13. Okay? Which simply means the ordered pair 2, 3 in R2, in the plane, in the xy plane, maps or is assigned the real valued number 13. That's all it means. So anybody remember what this would graph to look like? This is, remember how I said this is going to be somewhat of a review of chapter 12 stuff? No, it would need a z squared for it to be a cone. So you were close. It's an elliptic paraboloid. The quick graph of an elliptic paraboloid, it's actually, that ellipse is actually a circle. And the quick graph, it opens upward. It would look something like this. If you're just after a quick graph, and this vertex would be, which point? 0, 0, 0, the origin. 0, 0, 0, say that 3 times fast. 0, 0, 0, 0. I think I did it. So let's let g, now we don't have to use f all the time. Let's let g of xy equal the function square root of 36 minus 9x squared minus 4y squared. what could you always replace the function notation with? In a two-variable function, replace g of x, y with z. And then I think if you square both sides, it'll help you recognize it. So if you square both sides, do you see that you get z squared is equal to 36 minus 9x squared minus 4y squared? Does everybody see that? Furthermore, well, you guys, I want to ask you, any suggestions on how to make this very recognizable? Could I leave the 36 by itself? Yeah, okay. So you're telling me to move this stuff over to the other side. And I like that suggestion. Let's do that. That'd give me 9x squared plus 4y squared plus z squared equals 36. Oh, there we go. Okay. So one more step to put this in a standard form of one of those quadric surfaces. What could I do? Get 1 on the right side, so divide by 36. And I end up with what? X squared over 4 plus y squared over 9 plus z squared over 36 equals 1. You guys recognize this? What is it? I like that. It's an ellipsoid. It's one of those football or egg shapes, right? Ellipsoid. All right, so how are we going to graph this thing? Well, this is more good review for the exam coming up next week. Just graph the egg shape without the coordinate axes and put in the coordinate axes later on. And you're going to have to erase part of it. Okay? We'll talk about that in a second. It's not going to be, if you look at the original function, it's not the entire egg shape. It's only half of it. But you might like this way of graphing it. So I'm going to graph, let's see. It looks like the long axis is going to be along the z, right? So I'm going to graph this guy as kind of my equator or prime meridian or whatever you want to call it. And then I've got to have, so that's a trace in the computer screen, right? In the plane of the computer screen. And then I'm going to have a trace, a vertical trace coming out like so. Another vertical trace coming out like so. And then the true equator, I guess, would be like that. And then what part of it, now go back and look at the original function, you guys. What part of it has to be erased? Z is only allowed to be positive. And when you draw this, the origin is right there in the middle. Well, can everybody see what I was pointing at? When you draw this, the origin is right there in the middle, right? So are you allowed to have any of this bottom half at all? No. It's the because of the square root, this represents the top hemisphere, if that's what it's called for an ellipsoid. I'm not sure. But let's say the top part of an ellipsoid. So that means I've got to do some erasing. So I'll just go like this. And then let's put in some relevant details. Let me put in the z-axis, positive z-axis. I think I'll make the x go like this. So if this is positive x, where does positive y have to point? Into the screen, right? To keep it the right hand orientation. So like that. So that's positive y back there. And then so let's put in a couple of points here. What would this point be? What's the length of this axis right here? Have to be 6, the square root of this number, right? So 0, 0, 6 would be that point. What would this point be? It's on the x-axis, so it'd be the length on the x-axis out to here. What would that be? 2, the square root of that number. So 2, then the rest of them, since it's an intercept, is the rest of the other coordinates are 0, right? And then what would this, say this y coordinate be? It's got to be negative, right? So it's got to be 0 something 0 because it's the y coordinate, negative 3 because that's the negative direction. There you go. That's enough information to tell me that you know what you're doing by putting in that information. Okay? So there you go. There's the graph of your function. To find the domain, let's set the radicand bigger than or equal to 0. So what was it? 36 minus 9x squared, was it? Minus 4y squared? And then greater than or equal to 0. So what's a nice way to write this? If you think of it as an equal sign, so the border, you'd get the border, equal gives the border, right? The boundary of what's in the domain and what's outside the domain. So what kind of object would that be when it's an equal to instead of a greater than? It would be an ellipse. And by the way, you can tell that when you set z equal to 0 here, right? You can tell that the border is an ellipse. Okay. And from this picture, right? In fact, the domain is kind of included in this picture, but that won't always be obvious. Okay, and it won't always be the case either. Okay, so let's do this. Let's get the minus 9x squared minus 4y squared over to the other side. And then if it'll have to be less than, if I turn things around, would you agree it would look like that? I moved essentially the 9x squared plus y squared to the right side, but then I switched the right and left sides. Does that make sense? And then to put it in standard form, if this were an equal sign, we'll do what we did earlier, right? Divide by 36. So we get, what, x squared over 4 plus y squared over 9 is less than or equal to 1. Would you buy that statement? All right, so let's graph this domain. The domain then, if you graph it, is going to be in the xy plane, and it's simply graphing the border and then shading appropriately. So the border again, if you put in an equal sign there, the border is an ellipse with center 0, 0, and how far do you go out on the x-axis? You go out 2 in both directions from the center, and on the y-axis 3. And so it would be a solid border because it's less than or equal to. So just a solid ellipse going through these 4 points. And then remember, when you're solving these kind of inequalities, you shade on one side or the other, because this border breaks up the xy plane into 2 regions. The region inside the ellipse and the region outside the ellipse. But because it's less than, when we rewrote it, which area or region is going to satisfy it? The ordered pairs from inside would represent the domain. And on the border itself, okay? So you can't, if you plug in any xy value out here, you're going to get a non-real function, is what I'm saying. Okay? All right, so how would you write this symbolically? I don't know if you remember it or not. Set builder notation. You'd say the set of all ordered pairs xy, the vertical bar means such that, and then just put in the inequality, such that x squared divided by 4 plus y squared divided by 9 is less than or equal to 1. So this is just saying, hey, all of the ordered pairs in the domain have to satisfy this inequality. It's just kind of a restatement in a different kind of notation of what the inequality is saying. It's called set builder notation. My math 60 students, intermediate algebra students, have trouble with set builder notation, but I have a feeling you guys will be okay with it. So symbolically, this is the domain, and then this is a picture of the domain. I like the picture better myself. Okay, and finally the range. Then you'll take a well-deserved break. The range, find the range. Okay, so look at the function, the square root of 36 minus 9x squared minus 4y squared. What kind of values are going to pop out of it? You know what? We've got a picture of it. How low does it get? How low do the z-values get? How high do the z-values get? From 0 to 6. There you have a picture of it. It's super quick. The range values would be y, not y, but sorry, I'm in the habit of teaching Math 60. In Math 60, it's usually called y. Would be z is between 0 and 6. And then if you put that in set Euler notation, it would be the set of all z values. Vertical bar means such that z is between 0 and 6 inclusive. That would be it. Or interval notation is nice too. 0, comma, 6, brackets, right? Same thing. Any questions on that? Okay. What if you didn't have the picture? I have a question. What if you didn't have the picture? Could you have gotten the range? Well, I mean, you could figure it out, right? Think about it like this. Okay, you look at, let me get my big eraser here. Hold on. Okay, so look at the function, and you think, okay, what's the smallest this could ever be? Well, I could think of a situation, so let me rewrite that as 36 minus the quantity 9x squared plus 4y squared. Does everybody agree I could do that underneath the radical? Does everybody agree that's okay, factoring out the negative? I could think there's got to be an x and y value. Since 36 is a positive number and 9x squared plus 4y squared is a continuous function, there's got to be an x and y value that you could put in for x and y and make that equal to 36, right? So I could think that, at least imagine that, oh, 36 minus 36, this could be 0, right? Square root of 0 is 0. But then I also know that if I plug in x equals 0 and y equals 0, for instance, that this whole part goes away, and the biggest this thing will ever get is the square root of 36, which is 6. So yeah, I can reason it out what the range would have to be, but it sure is easier using that picture, isn't it? Let's talk about a function from a numerical perspective, from a table, right? So this is a different kind of table than what you're used to. Let's take a look at it. It says the temperature humidity index gives the perceived air temperature as a function of the actual temperature T and the relative humidity H. And as you all know, if T, the actual temperature, is fairly high and H increases, it actually feels hotter than it really is, right? You guys have experienced that. High humidity and high heat are a bad mixture. So I can be written as F of T comma H. Okay, so I is the perceived air temperature given a particular actual temperature, air temperature, and a humidity. It's a function of two variables, isn't it? And when we say a function of two variables, we mean a function of two input variables. Okay, so here, now, well, my question is, how did somebody come up with these values? I don't know. Did they ask some dude, hey, how hot does it feel? And just take down the temperature? I don't know. But anyway, let's say for a second that this is valid. Then you can read this table. So you have the input, the first coordinate input values here, down this side of the table. So these are all T values. And then the second coordinate input values here along the top. So just to make sure you guys are good at reading this table, what would F of 9570 be? So you would go to a value of 95 for T, right? This is this is a T value, and this is an H value. So you would go to 95 down the first column of numbers, and then over to, along the top row, you would go over to 70. And if you think about it, if you made a cross where the two lines meet, so cross over, cross down, cross over from 90, cross down from 70, where the two numbers meet, that would be how hot it feels. Would you buy that statement? Let me get rid of those red lines. They're going to be in the way. So 124. Okay, so just to write it down separately, F of 9570, the output value is the 124. 124 degrees Fahrenheit. Always put your units down. Does that make sense to you? Okay, the next question is, what is the domain of the function? Remember, the domain has to be a set of ordered pairs. In this case, is the domain finite or infinite? Since we're just looking at the table, all we have to refer to is the table. The domain from the table is finite. So we could conceivably list them all, although I wouldn't want to, so we'll do it like this. The domain, so that's part A. Part B, we'll say the domain D is equal to a set of ordered pairs. Let's just get a pattern going. 80-20, 80-30, 80-40, 80-50, and then so on and so forth, right? And then after you get done with 80-70, it'd be 85-20, 85. I think you'll get the idea if I just say, oops, I lost my pen. If I just say 80-20, 80-30, just keep listing them all until you get to 170. 170 would be, if you go in the order I suggested, 170 would be the last value you'd get from this input and this input. So those are the possible input values. Would you agree with that statement? Okay. Part C. Now look at part C. Part C is interesting. It's going to be a useful idea to us in this chapter and throughout the class. It says, okay, for what value of H is f of 90H equal to 100? So we want the humidity. Given this output of 100 degrees and one of the inputs, can we figure out the other input? Kind of working backwards a little bit. What do you think? Yeah, so we're keeping the temperature constant, aren't we? So we're going to be looking just in this row, aren't we? Because we're keeping the temperature a constant 90 degrees, the actual temperature a constant 90 degrees. Which actually makes it a one variable function of H, doesn't it? If you think about it, since T is being held constant at, capital T is being held constant at 90 degrees, we've got ourselves a one variable calculus 1 type function in table form. Anyway, we know the output is what? It was 100, right? So what H does that correspond to? 60. 60% humidity, right? So H would have to be 60% humidity. Now, what is that? I guess I didn't ask you to interpret it. Oh, I'll interpret the next one. Okay. So D, just a slight variation, f of 80H. Interpret f, I equals f of 80H. What is that? Well, it's actually a one variable function now, isn't it? So this is a one input variable. When I say one variable, I mean one input variable. Of course, there's an output variable as well. This is a one input valued function in the calculus 1 sense, isn't it? Let me add this. When T is equal to 80 degrees, so I'll put a comma, when T is equal to 80 degrees, I equals, you know, I'm thinking about it. I think I will make that a period. Sorry about that. I'll say this. When T equals 80 degrees, the function I gives the perceived air temperature for various H values. That make sense to you? Yeah, no big deal there. Okay, next we're going to talk about other ways to visualize a surface in space. So that starts with level curves. The level curves of a function of two independent variables, two input variables, are curves with equations f of x, y equals c, where c is a constant in the range of f. Okay? Otherwise, it wouldn't make a whole lot of sense to set f of x, y equal to c if it wasn't allowed to equal c in the first place. So let me show you an example of a set of level curves and why we care. So let's go just to something simple. Let's let f of x, y equal x squared plus y squared. And so let's set then f of x, y equal to different values of c. We're going to let c equal, we're going to let c equal maybe 1, 2, 3, and 4. And see what kind of picture we get for these level curves. So for c equals 1, we set, the idea is to set f of x, y then equal to 1. And I'm gonna turn it around and write x squared plus y squared then equals the c value, which is 1. What kind of object is that? Circle, right? In the xy plane, it's a circle. So let's graph that circle. Circle, center 0, 0, radius 1. So just drawing a freehand circle the best I can, which won't be that great. I had such a good start and then I messed it up down below. I needed to do a different color anyway. All right, not too bad. So that's your first level curve. In many situations, you'll label it. So if you think about it, for any x, y value on this level curve, you get that the z value is 1. So how do I want to label that? Z equals 1. I'll just label it c. I'll keep it c equals 1. But remember, c is a particular value of f of x, y, so it is a height value, isn't it? So every ordered pair on this curve corresponds to a height value of 1 when you plug it in the function. Okay. So c equals 2. I want to use c equals 2 because I want to make the distances between these constant values evenly spaced. So I plug in, I replace f of x, y with z equals 2, and I get x squared plus y squared equals 2. Now that's a circle, center at 0, 0. What's the radius this time? Root 2, right? Yeah, I did. Let me fix that. Hold on. Yeah, I meant to say 2 here, of course. And then, so here for the first one, the radius was 1, center 0, 0. What's the radius here? Root 2. So when I go to graph this one, let's see. What's root 2? About 1.4, 1.41. So looks like we're going to get a circle, a concentric circle with the first one. Looking something like that anyway, right? So that would be c equals 2. I'll fix the labeling in a second. And then c equals 3. So what would you get? X squared plus y squared equals 3. Center 0, 0. What's the radius? Root 3. Well, okay, root 3 is what? 1.7? Okay. So look, this circle is actually going to be closer, I believe, than the last circle. 1.7. So 1.5 is in here somewhere. 1.7 is in here somewhere. And I should have gone my spacing with my spacing a little further up with this one. Probably should have been up there, but That's okay. You'll get the idea. 1.7, something like that. So notice this circle is closer to the last circle than the last circle was to the first circle. Does that make sense? And then finally, when c equals 4, you get it's called a level curve. You get the level curve, x squared plus y squared is equal to 4. These are all called level curves or contour curves or contour lines even. What would the radius be in this situation? Center 0, 0, radius 2. And if I had drawn this, if I was a little more careful about it, you would see that this curve is even closer to the last one than the last two are. I should have made my spacing a little bigger, but I think you'll get the idea from this. Whoops, went a little off target there. There you go. Okay. So what do the level curves look like? The level curves that you get when you set f of xy equal to a constant, different constants, are concentric circles. And if you think about it, this kind of looks like the picture of z equals x squared plus y squared that I showed you a little bit ago on the grapher from above, doesn't it? Yep. So it's like you're looking at that bowl shape from above. Now the problem with level curves is I don't know if that bowl is upside down or right side up, right? Actually, there are ways to tell, but just looking at it like this, sometimes it's difficult to tell. And then if I wanted to label properly, I'd have to maybe go in and, since I didn't really make the picture big enough, maybe I could fix it, make it, let me use a really small pen here. Let's see. Okay. So make it c equals 1. And then what was this one? C equals 2, c equals 3, and c equals 4. So oftentimes you'll see the height values labeled like that, which then tells you that it's opening, that it's a bowl opening up, doesn't it? Let's look at some notes concerning these level curves. Note number 1. Although the graph of a function often gives a good representation of its general behavior, and fix it there. A sketch of level curves can often be easier to read in terms of specific values of the function and certain behavior. Now, how do you choose C? Choose C values that are evenly spaced to ensure an accurate depiction of the rate at which the function changes height. And it turns out that the more closely spaced the level curves are, the steeper the graph. So think of that bowl shape. Think of the graph of that bowl shape. It would look something like this, right? If you actually graph z equals x squared plus y squared, it looks something like that, doesn't it? Well, okay, it's steeper here on this trace than it would be, say, down here where it levels out at the bottom. And if you took other traces in between for evenly spaced height values, when you drop these traces down onto the xy plane, which is essentially what the level curves are, they're the traces compressed down onto the xy plane, the ones higher up for evenly spaced c values, evenly spaced function values, will be closer together. So you can see that here, these values, for the same distance between the c values, the ones out here are closer together than, say, the ones that we started with. And so the graph is steeper in this area than in this area. Okay? Closer together level curves indicate a steeper graph. What do we use level curves for? Well, topographic maps, right? So this part here is a topographic map. It has contour lines. Contours are the same as level curves. Contour lines show points that are at the same height values, right? Same C values. So if you think about this hill here and this hill here, if you look at it from above, then you look at the contour curves from above, you might get a shape that looks like this contour graph or this graph of level curves. And so these values here represent height values of the hill, right? Okay. What about where Z is temperature at a certain location? Right? You've seen this on the Weather Channel or some other channel. So here we call the contour lines or the level curves isotherms. And so on this isotherm or level curve, we have a constant temperature of 20 degrees. So it doesn't represent height here at all, does it? But it's still a function of location, right? So for this point in the United States, whatever this point corresponds to the temperature of 20, at this point the temperature is 20, right? So T of XY would equal 20 degrees. And same thing for every XY value on this curve. Isotherms, another application of level curves. What about isobars? That we're not as familiar with. Barometric pressure, right? If I remember right, it's measured in millibars. So here's a region of higher pressure out here in the Atlantic, I guess. Over Europe, we have low pressure, so maybe there's more clouds over here than over here, right? Oftentimes you have clouds associated with low pressure. So the isotherms don't necessarily correspond to height value. In fact, they're adjusted to be the pressure at sea level, I believe, if I remember right. And but they are a function of location, and the numbers themselves just represent how much air pressure is in that particular location at sea level. Make sense? So another application where it actually makes sense to draw contour lines. It doesn't even make sense to necessarily draw some kind of surface here, does it? So contour curves or level curves have lots of applications. Finally, level surfaces. We've reached the limit of what we can graph in space, right? But we can at least conceptually think of functions with more than two input variables, right? So what would a level surface be? Well, the level surface of a function of, this time it's 3 independent variables. Those are surfaces with equations f of x, y, z equals c. So you set a function w equals f of x, y, z, say, which doesn't have a graph in normal three-dimensional space, right? Because it has 3 input variables. How do you draw that? I don't know how. You can't. But if you set the function equal to a constant, like c, then that's actually going to represent a surface, and it will be a level surface of that function. So you can, and that's what basically the note says. The note says that you can get a glimpse of what a 4-dimensional object would look like, a function with 3 input variables, 1 output variable, using these level surfaces. It gives you a glimpse of hyperspace, essentially. So that's basically what the note says here. Okay, so let's do one quick example. That'll wrap it up for this section anyway. Okay, in this example, let's plot the level surfaces of f of x, y, z equals x squared plus y squared plus z squared. So this is a function of 3 independent or input variables. It's analogous to which of our quadratic surfaces? It's an extension of one of them. Which one is it an extension of? So it's, I'll put in parentheses, kind of like. Isn't it kind of like the f of xy equals x squared plus y squared? Well, we added a plus z squared on the end. So what is f of xy equal x squared plus y squared? It's an elliptic paraboloid. The horizontal cross sections are ellipses, right? So I've drawn this, I don't know how many times today, but something like this, right? That's probably the worst of the pictures I've drawn. This was supposed to be an ellipse, right? So maybe I went a little off track there. So maybe more like that. Okay. So that when you look at the level surfaces, level curves rather, of this object, what do we get? We just get in the plane, we pretty much drop down, we drop these horizontal traces down, and we get those concentric circles that we got earlier, right? But now, what are we going to get when we set f of x, y, z equal to constants? We're not going to get circles, we're going to get the three-dimensional version of a circle, which is a sphere. Okay, so I'm going to just do two of them because they get, as you might imagine, hard to graph level surfaces. I'm going to let c equal 1 and not 2, let's use 4 just because it'll be nice. So at c equals 1, we get x squared plus y squared plus z squared is equal to 1. What kind of object is that? It's a sphere. The center is 0, 0, 0. Radius is 1. How do you draw? What's the quick way to draw a sphere? So this is a sphere. Center, C for center, 0, 0, 0, and radius 1. How do you draw a quick sphere? Just draw the prime meridian. Draw the equator. And if that's all you're after, if you're just after a quick little sphere, there you go. Okay. And so that's a sphere radius 1, I guess. Okay, the center is 0, 0, 0. Okay, what if we have c equals 4? Then that's x squared plus y squared plus z squared is equal to 4. What's the center of that? Well, it's same. It's the origin, right? And what's the radius? 2. So, okay. Instead of getting concentric circles, we're going to get concentric spheres for the level surfaces, aren't we? So if we go out twice as far and then draw, I guess I'll do it in a different color. Draw the prime meridian. Not easy to do freehand. Might take a couple tries. I want to try and hit that point. Let's see. Well, way off. Okay, last try. Win, lose, or draw. I get 3 tries, right? We all get 3 tries. Getting serious about it now. Well, oh well. There we go. It might actually be easier to draw the outside sphere first because it's the bigger one. Right? Okay. It's actually not that bad. If I use my eraser here, get it a little more rounded right there, I should be in business. There you go. And apparently it's a glass sphere because I can see the one inside it. That makes sense? So we get our level surfaces are concentric spheres. These are like the cross sections, I suppose, in a way. If I could spell right, that would help. Of some 4-dimensional object that we can't really picture, right? But we can cut it and picture its, if you think about it, this is kind of trippy, we're picturing its cross sections as 3-dimensional objects.